Okay, so this is a video on linearizing data, which is an important skill that we're going to be using in AP Physics a lot this year. You should make sure you have with you a calculator, the PowerPoint itself, and something to write with while you're writing this, listening to this video or watching the video. So let me start with saying that what it means to linearize data. So linearizing means that you take any data that I give you, any formula, and you plot it so that what you end up with is a line. So even if the data is not linear, even if it's a quadratic, or if it's an inverse curve, or if it's a square root curve, or any, if you can think of any combination, any math relationship, you're going to plot it in a way that you get a line. And in order to do that, the way that you end up doing that is you just change how you're plotting it. You don't change the data because you can't make new numbers, but you alter it, you make changes to the data without changing the numbers themselves. And you plot it in such a way that you end up getting a line. So one of the things you're going to need to remember the whole time you're doing this is we're going to always be referring back to our equation for the line. And we're going to be using the slope-intercept form of the equation for a line. So we're always going to be looking at back to this y equals mx plus b, so we can remind ourselves what a linear equation looks like. Remembering that y, whatever's plotted on the y-axis, is going to be our dependent variable. I'll put dv, dependent variable. Whatever's plotted on the x-axis is going to be our independent variable. You're going to have to pardon my writing because I don't have my board, so I'm just having to use my mouse, which is not so good. And then our m value is going to be our slope. Oh Lord, that looks bad, but you'll get it. Slope, you just write slope. And then if there happens to be something added on, that's going to be our y-intercept. So for b, you're going to write y-intercept. And that's where it crosses over the y-axis. So on this graph right here, your y-intercept is 4, because that's where it crosses over. So I'm going to assume that you guys understand the equation of the line. You know how to find the slope of a line using rise over run. And you understand a dependent versus an independent variable. So why do we linearize the data? Why do we need to know this? One of the big issues you have with the AP test is you don't have a computer available to you. So when you need to use data to analyze data, sometimes it's difficult to do if you don't have a computer, because if the formula happens to be quadratic, or if it happens to be a square root, or if it's an inverse, there's not a really easy way to analyze data and actually use that data to determine anything. So one of the skills that we're going to learn is if we plot everything like a line, linear formulas are actually really easy to manipulate and easy to analyze. And finding the slope of a line is always something you can do even without the use of a computer. So if we linearize our data and we have everything plotted like a line and we know how to find the slope and we can figure out what the slope is equal to, then that will allow us to determine either constants or certain constraints or help us verify that our data is correct. The other really, really important thing that this allows us to do is it allows us to use the entire data as a trend rather than a single data point. Using just a single data point to try to verify your conclusion is never a good idea, because single data points can be have error in them, and they can be erroneous, and they might not be great data in and of itself. So whenever possible, we want to use the entire trend of all of the data to help us to verify whatever we're trying to determine. So we're going to do an example of this so I can show you how it works, and we're going to use the example of Ohm's law. And so Ohm's law should be something that you guys remember from last year. So I tried to choose an example of, first of all, a simple formula and one that you would probably remember. And so I wanted to remind you, I'm going to explain the experiment to you. Clara is running an experiment. She takes 6 different resistors. You can imagine she just has 6 different resistors. They're all different values. And she connects each one of them to a constant voltage source. So she has some constant voltage. And every time she connects a different resistor, then she measures the current. So she gets a data table where it has all of the 6 resistors that she measured and all of the currents. Let me remind you, I didn't put it here, but the symbol that we use for current is the letter I, and the unit is an amp. And I didn't put amps right here, but you should put the letter A all the way down. All of those are measured in the measurement of amps. Also remember that the symbol that we use for resistance is the letter R. So R for resistance, the unit is ohms. I for current, the unit is amps. So we have to ask ourselves, before we begin to linearize anything, what's the independent and what's the dependent variable? In this case, the independent is always the variable that the experimenter gets to pick. So in our case, the experimenter chose the resistors. So therefore, that's the independent variable. The dependent variable is the one that you measure that changes as a result of the resistors. So in this case, it's the current. So our two variables, we have one independent and one dependent. So when we go to plot them, if we think about this, we would be plotting the I, something I related on the y-axis, so that's where dependents get plotted, and something R related would be on the independent axis, since that's where those get plotted. The next question says, what relationship does the data appear to have? So when we look at the relationship that the data has, if we just look at it, you can see that the resistance tends to be getting higher and the current tends to be getting smaller. And so we would say it's some sort of relationship. We don't know exactly what it looks like. It could be a negative linear thing where it gets less and less and less, or it could be an inverse. We're not sure. But we definitely have one getting larger and the other getting smaller. So then we start thinking about formulas that we might have that relate resistance and current. And that's what brings us to Ohm's law. So it's going to be important to know the physics so that you know what formula you have to look at. So if we think about Ohm's law was written as V equals I times R. That's how we wrote Ohm's law. But we want to try to relate the current and the resistance, and how are those two things related to each other. And so you can think about it. If we try to keep the V constant, then the I and the R have a relationship where if the I gets bigger, the R is going to get smaller, so that when you multiply the two of them together, you get a constant V. If I rewrite this so that I put the I, which is the dependent variable, on the left and solve for I would have I equals V over R. And that's going to be something that you have to get used to doing, is writing it so that the dependent variable is on the left and everything else is on the right. So the dependent on the left, everything else on the right. And you can see clearly that there's an inverse relationship here. The R is it's a 1 over R relationship. That's an R on the bottom. I know you can't tell it, but it is. So an inverse relationship right here. And can we use the trend of data along with our knowledge to determine what the voltage would be? So some students would want to go right in and they'd be like, I'm just going to pick one of these data points and plug it in and solve. The problem with picking a single data point is that you don't know if this is a good data point. This might be an error. Or if I just chose this one right here, you actually don't know if that's a good data point. So what you need to do is you need to try to graph the trend and see if we can use the entire trend of all of the data. That will help us get rid of bad points to figure out what the voltage is of the source. So that's where we're going to end up using linearizing data to help us determine that. Because right now, if we plotted it, it would not plot up as a line. In fact, if I plot it, it actually plots up as an inverse curve. So you can see that this is in the form of an inverse right here. And we could predict that. We actually did predict it because we looked at Ohm's law and we saw that it was I equals V over R, and that's an inverse relationship. As the resistance gets higher and higher, you would expect the current to get less and less because of the mere definition of what that is. So this is actually the plot. The problem with this plot is that we cannot figure out voltage using this entire trend. There's really nothing I can do, especially if I don't have a computer, to analyze a curve like this. I can't really hand sketch a best curve. I can't really do much with it. And that's why we're going to linearize the data. So what we would need to do is we'd rearrange the formula until we get into that format of y equals mx plus b. So we did that part already because the y variable, remember the y variable in our case was going to be the current. That's what we were going to have as our dependent variable. The x variable, in our case, was going to be the resistance. So I wrote it in the form of I, which is going to be my y variable, equals V over R. Okay? So that's in the form. It may not look like it, but it's in the form of y equals mx plus b if we kind of do a little bit of rearranging. So if I look at this and I start comparing it to y equals mx plus b, and I look at those comparisons, I want you to watch how I do this. First of all, I need you to recognize there is no plus b. There's nothing added out here. So this term we're not going to worry about because there's nothing added on here. So now I have to figure out, how does this look like? How does y equals mx look like this thing right here? So I think a little bit easier to understand is that the I and y are the same thing. So that's pretty easy, right? Because you see y is my dependent variable, I is my dependent variable. I'm good to go. The next thing I'm going to do is I'm going to take the r, which is my independent variable, and I'm going to move it over to the side. So I'm going to write this as I equals v times 1 over r. It's the same thing, I'm just pulling the r off to the side. I'm doing this because this actually starts to look more like y equals mx, and remember I've ignored the b because there's no b. So now if I look at these and I start comparing them, I can see that the y is going to be my current, and on my x-axis I can actually plot 1 over r. So I'm varying the r itself. I'm plotting 1 over r, and my slope, if I do that, my slope should be the voltage. So that's how we're going to end up linearizing data. So we're going to do this a lot of different ways. We're going to look at a lot of different formulas. We're going to be putting the dependent variable on the left. We're going to pull that independent variable off to the side, leave a bunch of other stuff here in the front. All the stuff in the front is going to be the slope, and whatever form the dependent variable takes, that's what you're going to plot on the x-axis. So if we were to take that data back from the previous slide, so I'm going to go back to this previous slide for a second, look at this data. I have all of these currents and all of these resistances. I would actually end up making another column. I could do it right over here to the side. I could make a column of 1 over r. And I would just do 1 over 10, which is 0.1, and 1 over 15, which is whatever 1 over 15 is, I think 0.07, and 1 over 20, which is 0.045, I think, and 1 over 25, which is 0.04, right? So I'm just taking these r values and doing 1 over. These are what I'm going to end up plotting on the x-axis in order to linearize my data. So I'm no longer plotting resistance on the x-axis, I'm plotting 1 over. So when I do that, this is what I end up getting. I plotted 1 over r down here, so you can see these are my 1 over r values, and there's my regular current. I didn't change the current at all, and I end up getting a line. So now I've taken something that, if I scroll back, that was inverse, and I've plotted it in such a way, without altering the data itself, I've plotted it in such a way that it's linear. So what ends up happening now is I can take my, if I wanted to, I could take 2 data points that are on my, I could draw a best fit line. So what I would end up doing is I would take my, the best I can, draw a best fit line through this, use a ruler, whatever you got to draw the line that kind of goes through as many data points as you can get. Then I would pick 2 points off of my best fit line, so 2 points that I might like. I might choose this one, and I might choose this one right here. And I would do a rise over run, a y minus y over x minus x, rise over run, and I would figure out the slope. And in this case, whatever slope I ended up getting, that would be my voltage. Because when we looked at that formula, the voltage was the slope. So this is a process that we're going to be using a lot of. I'm going to stop you here because we're going to do the next one. This one here, the distance that objects fall, we're going to do this one in class together on Monday. But I wanted you to just be introduced to this idea of linearizing data.